Excellent. I appreciate everyone joining me today on the Zoom chat. As advertised, my name's Peter Delfyett. I'm from Creel, College of Optics and Photonics. My contact information is here. I'm in my 28th year at UCF, and prior to UCF, I've been at Bell Communications Research for 5 years, and there are some pertinent data on the left side of the screen. The general philosophy of my research group is sort of an application pull kind of a concept. We take a look at systems that we want to make an impact in, and then by looking at the bottlenecks, we try to understand the fundamental physics associated with bottlenecks, develop new devices, insert them in systems that will ultimately have better performance. If you ask us what I do the 5 M's of photonics. We work on technologies that make the light, modulate the light, multiplex the light, move the light, and measure the light. This is basically generation, modulation, multiplexing, transmission, and detection. One of the key technologies that we have are these mode lock lasers, which are the devices which produce a very short optical pulses in a very stable manner. These periodic electric fields are so perfectly generated that their optical spectra are in fact periodic as well. Since the repetition rate is high, the different colors in the laser are sufficiently far apart that we can filter and have access to these individual colors. More importantly, there is a well-defined phase relationship. This becomes a coherent bank of local oscillators that we can use in many applications of communications and signal processing. Some of the things we're noted for are the world's shortest pulses from diode lasers, the world's highest pulses from diode lasers, the world's most stable clock from diode lasers, and record-breaking or setting communication experiments. Regarding short pulse generation, as you try to generate femtosecond pulses from diode lasers, many nonlinear dynamics come into play. These ultimately create situations where if you take a look at the impulse response of the amplification medium, it has a mechanism which tends to take the input pulse and broaden it. So as the pulse gets shorter, this nonlinear dynamics puts a braking motion and basically rips the pulse apart. With lots of thinking, you eventually determine the best way to get around this or engineer around the laws of physics is to have 2 types of dispersion modules, one to stretch a pulse so that these nonlinear effects are not introduced with an amplification, and then you recompress the pulse so it can interact with nonlinear media that will further shorten and broaden the spectra. This breathing mode kind of concept that we developed, we're able to generate optical pulses of about 180 femtoseconds in duration. These are the world's shortest pulses at the time. To give you a feel, the physical length of these pulses are about 60 microns in length. They have a spot size of a few millimeters and fly around the room at the speed of light. The government then came to us and said, can you make lasers like this that blow holes through walls? And we said, gee, that's going to be quite challenging. Many people try to take the gain medium and open up the gain stripe or to make the area larger. We came across with a completely different idea, which said, recognize that the semiconductor gain is very much like a leaky capacitor. And so if we could basically take our femtosecond pulses and stretch them to many tens of nanoseconds so the temporal duration is longer than the RC time constant or storage time of the gain media, the optical pulses going through the gain media will look quasi-CW. We perform this technique, and with picojoule input optical pulses of about a half a picosecond in duration, we take these optical pulses and stretch them with chirped fiber Bragg grating, which takes half picosecond pulses and converts them to 10 nanosecond pulses. This is a 20,000 to 1 stretch compress ratio. The stretch pulses are amplified once, twice, and recompressed back in this fiber. This was so attractive, we basically got half picosecond pulses with kilowatts of peak power. We further implemented the system to get over 1 microjoule of energies in these short optical pulses, and this kind of energy can in fact blow holes through walls. We then spun a company out of the UCF technology transfer program. That company was called Radiance. Some of the specs of the company are shown here. It was recently acquired. Another thing we're well known for is optical clocks. And so the general concept is you can make a well-defined oscillator with an infinitely high Q as long as you don't take energy out of the oscillator. That's a useless oscillator. So a trick we found is by incorporating nested cavities. You take a large optical ring, a fiber laser, that's producing optical pulses. This ring has a periodic sort of Fabry-Perot structure. These are these narrowly spaced optical frequency combs. By inserting an ultra-low expansion quartz cavity, which has a much wider free spectral range or frequency spacing shown by the dotted curve, If you harmonically relate these things, the product of the two transfer functions is shown here, retaining the narrow cone lines of the long storage time of the cavity, but the wide frequency spacing associated with the short cavity. The key trick is that the insertion loss of this cavity is basically zero because it operates on resonance. This is why you're able to still extract the same amount of energy without affecting the Q. We can build these things up with Koch components, insert them in boxes and move them around the country. Some of the performance parameters are shown here. We have 500 different colors in the C-band of the telecommunication window. These pulses are less than the trillionth of a picosecond in duration. They have timing stabilities of less than 1 femtosecond measured out to 1 second. The line width of an axial comb tooth, one component, is on the order of 1 hertz, and the optical frequencies are stable to around 70 hertz over a measurement period of around 30 milliseconds. These are some of the power specs and characteristics shown here. Very good. Another thing we like to do is to utilize the different colors of the optical frequency comb. Pulses which are periodic in time, their spectra are periodic. Second semester calculus says Fourier series works. Manipulating the amplitudes and phases gives us the ability to synthesize the electric field. By taking a mode lock pulse and separating the colors and having modulators on each individual color, we only need modulation bandwidths that fill the frequency spacing here. So on a 10 gigahertz comb, by having 10 gigahertz modulators with literally hundreds of frequency comb components, I could get terahertz wide instantaneous bandwidth synthesized using only 10 gigahertz electronics. How do you measure signals like that? You take a secondary frequency comb and literally down convert color by color into the RF domain, low pass filter, and you can see the actual electric field envelope and the carrier frequency, in this case, chirp pulses, FM swept pulses, or compressed pulses. So you really get a picture of the electric field. These pulses in real time are 100 picoseconds apart, down converted to about millisecond time scale so you can observe on slow scopes. We can synthesize pulses however you wish. This is the classic sing squared, where you have a flat rectangular spectrum with flat phase. We can generate the Airy function pulse, which has a comb flat rectangular shape with a cubic phase. We can chop the phase back and forth for period doubling, and we can put cubic phase also on one of the pulses to do stretch pulses. So we can synthesize whatever you want. Literally electric field via the Etch-a-Sketch method and synthesizing the electric field. What are we doing now? We're taking CW lasers and pumping silicon nitride-based microcombs to generate curved frequency combs. They're shown here. We're using these as conventional wavelength domain multiplex communication systems. We have 13 channels in C-band. We're modulating each channel at a 20 gigahertz clock rate, PAM4. That's 40 gigabits per second per channel. Right now we have about a half a terabit per second from chip scale optoelectronic components. Another nice feature, these micro ring combs basically are on a wide frequency grid. Many times it's difficult to sort of measure the repetition rate or timing. So what we do is we lock this thing to an atomic reference and we overlap the comb spacing of the micro ring resonate with that of a passive mode lock laser. Using injection locking techniques, these colors lock this lower repetition rate laser to basically coherently synchronize the colors of this lower rep rate laser to the micro ring source in the atomic reference. Here we're down converting a 150 gigahertz clock to 10 gigahertz. Look at the dramatic reduction in phase noise. This is the optical setup. We get an improvement in timing stability of about 5 orders of magnitude, of about 10 to the minus 7 at 1 second to 10 to the minus 12 at 1 second on a 10 gigahertz carrier. What's in the future? We're basically making mode lock lasers with some money from NIH to make hopefully semiconductor-based microscopes that can have sub-diffraction limited imaging. We're also taking these kind of tabletop world, performing laser systems and putting these things on chips. We've done this, and we're trying to integrate mode lock lasers, nonlinear optical elements, optical filters, etc., all integrated on a common chip. And finally, a little movie that shows this non-thermal ablation that we spun off to radiance. Here we're showing the laser literally blowing off the phosphorus without any heat whatsoever. The glow you see is the plasma fume created by these sub-picosecond pulses blowing the electrons off atoms and the residual phosphorus atoms being ejected. So we're able to remove material without deposition of heat whatsoever. and this technology was used to make medical stents, drill holes in fuel injectors, and cut the gorilla grass in the Samsung phone. Thank you very much. Hope to hear from you guys soon.